This is video 1 for the circuits unit. So for this one, there's only two big ideas. Objects and systems have properties such as mass and charge. Systems may have internal structures. So we're going to focus in on the charge part. This objects and systems have properties known as charge, and the internal structure of the system will be the things we have inside the circuit. So the whole circuit will be the system. Then big idea 5, changes that occur as a result of interactions are constrained by conservation laws. We're going to focus in on conservation of energy and conservation of charge when we take a look at circuits. So the learning goals for this one, I want you to be able to choose and justify what data is needed to determine the resistivity for a material. I want you to be able to apply conservation of energy in calculations involving electric potential differences for complete circuit loops. That's going to be a lot easier than you think. I want you to be able to use a description or some sort of diagram of a circuit to calculate unknown values of current within the wires. And then I want you to be able to apply the concepts of power to electrical circuits. We'll do lots of practice with this, so it's really not too bad. Let's begin by talking about resistance. Materials have a property that's known as resistance. The resistivity of a material then will depend on its molecular or atomic structures. So remember that electrons of different atoms have different degrees of freedom. So in metals, room temperature heat energy, that's enough to cause the valence electrons to leave the atom and kind of float around. So what we have is the sea of electrons, where we have electrons just kind of going from ion to ion to ion. Materials like glass, however, keep all of their electrons closely attached so that the electrons have no or very little degree of freedom. So then this relative mobility for the electrons is what's known as electric conductivity. Materials with high electron mobility are called conductors, while materials with low electron mobility are called insulators. So here's a quick little graphic showing you going from insulators to conductors. We also have semiconductors in the middle. Now for many ways we can use water as an example for electrical values in electrical circuits. So I want you to think about water flowing through a pipe. And I want you to think about ways that you could slow that water down. So one thing we could do is we could try to make the pipe narrower. That would definitely slow the water down. We could also make the pipe really, really long. A very, very long pipe, it's going to take a lot of effort to push all the water through a very, very long pipe. So a very long pipe would have a very high resistance. Or maybe we can change the material. Instead of water, maybe we can have syrup flowing through. Probably misspelled that. Or molasses or something like that, something more viscous. That would have more resistance. So those are kind of the three ways to increase the resistance. We can try to make the pipe narrow. We can make the pipe long. Or we can have more viscous material. Again, I probably misspelled that. So for electricity then, the model we use to calculate resistance looks like this. So in this one, rho is the resistivity, and it has units of ohm meters. L is the length of the wire, has units of meters, and A is the cross-sectional area of the wire. units of meters squared. So if I take a wire, notice that the longer the wire is, the more resistive it is. The fatter the wire is, the larger the cross-sectional area, the less resistive. The narrower or the skinnier the wire, the more resistive it is. And then the resistivity is just the property of the material. Different materials are going to have different resistivities. So let's take a look at some of these. I'm going to add some to this list here. Silver is 1.59 times 10 to the negative 8th. So that's the best. Silver is the least resistive material, or least resistive metal. But there's one above that, carbon. But we have to be careful. It has to be graphene. So carbon in its graphene form has a resistivity of 1 times 10 to the negative 8th. Copper, 1.68. So notice that copper is more resistive than silver. So it makes you wonder, why do we use copper to wire our homes and not silver? I'll let you ponder that, but you probably already know the answer. Gold. Don't be fooled by the commercials that tell you that a certain earbud or a certain headphone has gold wires and that makes it better. In fact, gold is more resistive than copper. Aluminum, 2.65. Tungsten. Tungsten is the material that you find in your toasters. So it's the wire filament in there. It's also what's used in light bulbs, and it's actually relatively resistive compared to other metals. So it's really going to convert the electrical energy into heat, and that's really what a resistor does. A resistor converts electrical energy into heat energy, and if you convert enough of it, if the material gets hot enough, it begins to glow at a certain color. Now, I'm going to add one here, iron. Iron is 1 times 10 to the negative 7th. That kind of goes right here. So iron is more resistive than tungsten. Nichrome. This is an alloy of nickel, iron, and chromium, I believe, or chromium. And that alloy has resistivity of 100 times 10 to the negative 8th. Or I guess you could say maybe 10 times 10 to the negative 7th. Carbon. Now, for this one, we're talking about the graphite form of carbon. This is the carbon that's in your pencil lead. This is 3.6 times 10 to the negative 5. So it's actually fairly resistive. And notice then that what that means then is that carbon can either be the least resistive or it can be relatively resistive. And it depends on how those bonds are formed. Glass is a little different. It's 1 to 10,000 times 10 to the 9th. Now notice we're making a huge jump here. Now we're suddenly going from conductors into insulators. Teflon. Again, once you get to the insulator one, it's kind of hard to get a real accurate measurement of how resistive it is. Teflon is very resistive. Mica. Mica is kind of a gem or a material, or a rock, if you will. It's very, maybe not quite as resistive as Teflon, but still pretty resistive. Hard rubber. hard rubber is anywhere from 1 to 100. So again, not quite as resistive as Teflon, but still it's an insulator. Seawater is 2 times 10 to the negative 1. So it may be something kind of shocking. Distilled water is 1 times 10 to the 10th. So distilled water is almost as resistive as rubber. And then carbon in its diamond form is 1 times 10 to the 12th. So those are just some examples of resistivities. And again, remember that the purpose of a resistor is to convert electrical energy into thermal energy. And that's what a resistor does. So the more resistive a material is, the more it converts electrical energy into heat energy, which is why it's so important when you wire your houses that you choose the correct wire, because the wires can get hot. Now, while the normal motion of free electrons within a conductor is random, we can influence the electrons to move in a certain direction. So we have to go back to the last chapter and think about electric potentials. So electrons will move toward higher electric potential. Now remember, electric potential is voltage. So, for example, if I have a 9-volt battery, so it's my 9-volt battery, the short little terminal is the positive end, the weird looking one's the negative end, and if I were to connect a wire to these, the electrons will move toward the higher potential. So the electrons would move in this direction back towards the positive terminal. And that wire then is a conductive material with a low resistivity. Positive charges, if they were to exist, positive charges move toward lower electric potential. So again, to do this, we need to provide a path for the electrons to follow. This is a wire. Wire is a path for electrons. Wires that we use are typically made out of copper that are surrounded by a rubber casing. The path cannot have any breaks. If we introduce a break to the path, the current or the electrons will stop moving. So if we want the electrons to move continuously, we need something called a circuit. So a circuit is a continuous path. So let me introduce some symbols here. This is the symbol for a battery. The longer line represents the positive terminal. The shorter line represents the negative terminal. And so for this path, I put in something over here. This right here is called a resistor. So here we have our power, we have a resistor, and we have our path. So then electrons are going to flow towards higher potential. So the electrons are going to leave the negative side of the battery and enter the positive side. However, circuits were developed before we knew much about electrons. So the current is going to flow from the positive to the negative. We say that current is the flow of positive charges. Now I know that positive charges cannot move. The, the way that we kind of explain this is, again, this was developed before we knew anything about electrons. So we just assumed that positive charges moved. And what's nice is that all the math works, so it doesn't matter if this is wrong or not. But we go ahead and we say that this is going to be the conventional current. It's going to be the path that a positive charge would take. And again, this leads us to the new concept of current, where current is simply the flow of charges. The way that we find current is by counting how many of these charges pass a wire per second. So here are the charges, little Q's. We have them going past a cross-sectional area. And then the way we calculate it is we say that I, we use capital I for current, is delta Q over delta T. Or if we want to go into calculus, it's the derivative. Okay, that's going to finish up video 1 for the circuit.